All right, so if we remember in the last lecture, we had this slope field or direction field, and we could draw these solution curves. So the field represents one differential equation. Each solution curve represents the solution to an initial value problem, which is the differential equation with some initial value, usually y of 0. You could give y of some other value. That's fine. This is just a sketch. So before we solve any differential equations, we're going to talk about a method that basically uses the ideas here that will give us an approximate solution to a differential equation. This is one of many numerical methods to solve differential equations and is very useful in differential equations that don't have a closed form solution, one that we can solve analytically. So our example, we will actually use one that we can solve analytically because then we'll be able to check how close the approximation is. But most of the time we would use this method for one that we can't. So I mentioned this equation in the very quick first lecture on intro to differential equations. And remember, I said we could maybe guess the solution, like what function's derivative is itself. Well, probably something like y equals e to the t. That's not going to be the only solution to this differential equation, because as we saw, we could draw some sort of slope field, and we should be able to get infinitely many solutions. So that won't be the only solution. Maybe if you remember a little bit of integral calculus and how that works, you could guess some more solutions. In the next lecture, we'll talk about how to actually solve it analytically. Now, that's just the differential equation. If we include both of these, now we have an initial value problem. This is actually the solution to this initial value problem, because if we check, e to the power of 0 is 1. Okay, so this is actually the solution, so keep that in mind. Okay, but pretend we weren't so clever. We weren't able to guess that in our whole lifetime, and all we had were numerical methods. So here's one of the crudest numerical methods, and this is Euler's method for approximating solutions to differential equations. So we're going to have an axis, t and y, and let's say we start at, so this is 1, 0, we'll call this 1. I like having the ones be the same scale unless it's absolutely ridiculous. Obviously, if y of 1 is 1,000, then you won't be able to do that, but this helps you see what the actual slope is. Okay, so we're going to plot this point. We'll plot the point y of 0 is 1, right there. And then we're going to calculate y prime of 0. Okay, so y of 0 is 1, and then y prime of 0 is equal to y, so it's also 1. So now you have a slope of 1, and then we have to decide on a delta t. So for simplicity, we're going to also use delta t equals 1. The smaller delta t is, the more accurate your solution is. This is a common theme in calculus, right? You increase your change, and then suddenly approximations become exact. As the limit, if we take limit delta t goes to 0 from the right, so it stays positive, then solutions become exact. Otherwise, they're approximations. So 1 is pretty large. This is going to be a pretty, this is going to be a lot of approximation, and we'll see that. Okay, so if we just go for our delta t is 1, we're going to take a slope of 1. So we'll just draw a line segment of slope 1 from there. And our approximation will tell us that y of 1 is approximately 2. Okay, then let's keep going. So now we're at t equals 1. So we say y of 1 is approximately 2, which means y prime of 1 is also approximately 2. Okay, and then our delta t is still 1, so we'll go one more. We'll go up to 2. We're going to draw a line segment of slope 2. And then we'll get, so we started at 2, slope was 2, so we should land at 4. So y of 2 is approximately 4. And then y prime of 2 is also approximately 4 because y prime equals y. Okay, delta t is still 1, so we're going to go up to 3. We'll have a slope of 4, so we'll end here. Change in y over change in x is 4. Okay, and that brings us to 8. And then we can keep going. Our next one would be y of 3 is approximately 8, and y prime of 3 is approximately 8. And we don't have to graph every time, right? So this is going to run off my graph, so I can calculate my y of 4. What am I actually doing here? I'm taking my y of 3 value, and I'm adding the slope, so y prime of 3 times delta t, right? And these numbers are easy. This is 8 plus 8 times 1. Okay, so y prime, or y of 4 is approximately 16. Okay, and then let's just go back and look how close we are. So here we have e to the t. What is e to the 4? So y of 4 is approximately 16, we said with Euler's method. Y of 4 is actually e to the 4, which is a little bit bigger than 54. So this is a bad approximation. Why is it so bad? Well, let's think about that. Let's check what y of 1 actually is. That's e to the 1, which is about 2.7. Okay, so that was already bad, but not as bad. Here we're off by over a factor of 4. Here we're off by less than 50%. Why does it get so bad? Because every time the error keeps accumulating. Once we have y of 1 is approximately 2, we're just now assuming it's 2 from then on, right? Because our change in y to get y of 2 is assuming that y1 was exactly 2. Whereas if we instead used 2.7 here, this would no longer be Euler's method, but that would be a little bit better of an approximation if we could somehow know what that was. Maybe we can't. So the error accumulates over every interval you use, and it gets worse and worse and worse. So with Euler's method, especially with a large delta t, you probably don't want to go on for too long. It's a little cumbersome to do by hand, but you can do it. We won't make you do it too many more iterations than this, certainly by hand. If you're familiar with Python, in the resources for the class, there are several technology resources at the end. There's some Python code that you can look at and program, and you can play with it. Delta t equals 1 was not good, and there you could put delta t equals 0.001 or something. The computer can do it very quickly. We're not going to do 1,000 things by hand. And maybe with this differential equation, with this 0.001, we could actually, going from 0 to 1, we could get close to a value of e for y of 1. So check that out if you want.